So we're going to work through another ratio test example here, and this time the example is going to have a factorial in it. So remember, the ratio test is useful when we have some number raised to an n value or some sort of n factorial. That is when we try the ratio test first. And just to review, what we're going to do is we're going to find the ratio of two terms, a term divided by its predecessor, absolute value, and whatever that absolute value nth term is, we're going to find the limit to infinity. And that limit to infinity, we'll call it rho. If rho is smaller than 1, it's fractional. We say it converges absolutely. If rho is greater than 1, we'll get a divergent series. And if rho equals 1, the test is inconclusive. Just a reminder what a factorial is. 3 factorial means 3 times 2 times 1. Similarly, 5 factorial would be 5 times 4 times 3 times 2 times 1. So if I was trying to calculate a ratio of factorials, say maybe I have 5 factorial divided by 3 factorial. Well, 5 factorial is 5 times 4 times 3 times 2 times 1. And 3 times 2 times 1 is 3 factorial. So when I have 3 factorial over 3 factorial, those are going to cancel, and this is going to simplify to 20, 5 times 4. Okay, so we're going to use a little bit of that logic, but we're going to have some n's in there as well. I just wanted to make sure we knew how to handle our factorials and how to simplify these rational expressions with factorials. So let's skip to our example. So let's investigate the convergence of the series from 1 to infinity of the quantity 2n factorial divided by n factorial times n factorial or n factorial quantity squared. So because we are investigating convergence and we are dealing with factorials, factorials let us think, hey, let's use our ratio test. So in order to apply the ratio test, I need to know what my a sub n plus 1 term looks like. I have my a sub n term, that's my general term. My nth term would look like that. But what does a sub n plus 1 look like? So that would be 2n plus 1, that entire quantity factorial, over n plus 1 factorial n plus 1 factorial. So let's set up our ratio here. Absolute value of, I'm going to distribute right there. So that's 2n plus 2. So I've got 2n plus 2, that quantity factorial, over n plus 1 factorial n plus 1 factorial. And I'm going to divide that by the term which came before it, which would be 2n factorial over n factorial n factorial. So division by a fraction is the same as multiplication by a reciprocal. So this turns into, I'm going to have n factorial, 2n plus 2 factorial over n plus 1 factorial, n plus 1 factorial, and 2n factorial. So I multiplied this and I used commutative property of multiplication to rearrange it just because I know I'm going to want to look at these ratios in a specific way. So I'm going to look at simplifying one of these as well as this guy. All right, and in order for us to simplify what those ratios of factorials would look like, it's helpful for us to write out a few terms. So what does n factorial look like? N factorial looks like n times n minus 1 times n minus 2, n minus 3, all the way down till we get to multiplication by 1. Okay, so a factorial, like 5 factorial, we would say 5 times the term before it 4 times the term before it 3. So that's what that n minus 1, n minus 2 are. So what does n plus 1 factorial look like? So working through this, I've got n plus 1. Take away 1 from that gives me n. Take away 1 from that, n minus 1, n minus 2. Multiplying all the way down until we get to just 1. So if we look at this as a ratio, what we notice here is that n over n cancels, n minus 1 over n minus 1, n minus 2 over n minus 2. Everything following this is going to cancel all the way down till 1. So this simplifies and this turns into 1 over n plus 1, and the factorial is gone. All right, so this right up here, I've got 2 of these that I've just simplified. So I'm going to be able to plug that in for both of those and reduce this down. Okay, so let's look at our other piece here, which is this guy. So I'm going to list out my factors for 2n plus 2 factorial. 2n plus 2 factorial. So that's 2n plus 2, take away 1, 2n plus 1, take away 1, 2n, take away 1, 2n minus 1, multiplying all the way down to where we multiply by a 1. And if I look at 2n factorial, that is 2n, 2n minus 1, and I see that 2n minus 1 up right above on the row. So this is going to multiply all the way down to 1 as well. And when I look at what I can cancel here, I notice 2n over 2n, 2n minus 1 over 2n minus 1, all the way down to 1. So this ratio is actually going to be equal to 2n plus 2, 2n plus 1. So I'm going to rewrite what we had just so we can really see this simplification on the screen. We had in our absolute value bars up above, and I'm going back right up to here. We had n factorial over n plus 1 factorial. I had an n factorial over an n plus 1 factorial. And then I have 2n plus 2 factorial over 2n factorial. And I should have had parentheses up there. Apologize. So n factorial over n plus 1 factorial, what we have is that reduces to 1 over n plus 1. And I have another one of those, 1 over n plus 1. And the 2n plus 2 factorial over 2n factorial, that leaves me with, I'm going to condense these ones down here, 2n plus 2 and 2n plus 1. So we've simplified this and we've gotten rid of all of the factorials in there. So my ratio, I'm going to scroll back up for a second. This original ratio I set up and started with, this guy, using these properties of factorials, we now have this down as this term. This is my ratio. 2n plus 2, 2n plus 1 over n plus 1, n plus 1. And what we want to do is we want to look at this, the limit as n approaches infinity. So this is, now it's just a rational function. And we can factor and cancel to multiply it out, or we could just multiply it now. I do notice, looking at this, that n plus 1, there are 2 n plus 1s there. So I'm just going to say this is the limit as n goes to infinity. Multiply that 2 through that factor. I've got 4n plus 2 over n plus 1. And using our horizontal asymptote comparison test, since the degree of the numerator matches the degree of the denominator, we have a horizontal asymptote at y equals 4, which means the limit as we approach positive infinity is 4. And so in this case, this is equal to my rho value. And since rho is equal to 4 and 4 is greater than 1, we can then say this is divergent. Okay, so the function diverges.